attention-induced variance and noise correlation reduction in macaque V1, which is mediated by NMDA receptors. And so the things I'm going to talk about is not just NMDA receptors. I'm going to first give you an insight of what acetylcholine does with respect to various signatures of attention in V1, because it's very much contrasts to what NMDA does. And I will hopefully convince you that you can actually dissociate certain attentional signatures at the receptor level in primate V1. I will first talk about attention-induced rate changes, and that is mostly for contrasting reasons, because I want to dissociate that from changes in firing rate variance and in changes in noise correlation. And all these changes are attention-induced. I'm not going to give you a great overview of why I study attention, because I think for most people in the audience that is more or less understandable. And I'm also not going to give you a great insight into why I study acetylcholine and NMDA, because time just doesn't permit it. I mean, there is sufficient evidence or circumstantial evidence that either of these two substances have an important role in cognitive function and in attention, and that's why I used to study those. So the principle of the task is such that it's a covert attention task where the monkey fixates a fixation spot centrally. We map the receptive field of the neurons under study, which is highlighted here by the circle. We then present a cue briefly, which tells the monkey on this trial to attend to the receptive field of the neuron under study. We then, I'll try to see, oh yeah, this does work now. No, it's the wrong way around. Okay. We then present two stimuli, one in the receptive field of the neuron under study and the other one in the, oops, sorry. I'm trying to work out how the pointer actually works here. How does the pointer work?
It needs to be that way around.
That way around, okay. That explains it.
Guy. Yes.
Okay, thank you. Right. So on this trial, the monkey has to monitor this particular stimulus here and wait for a change at that location and ignore any changes that could possibly happen at this location. So on this trial, the change happens at this location first. Monkey has to ignore it and now monitor for changes at that location. And when it appears, he has to release a touch bar. So that's all there is. And obviously, on other trials, we ask the monkey to attend to the opposite hemifield. We present our stimuli in both locations again, and the monkey has to monitor this location for a change, and when it appears, release a touch bar. That's the task. And what we do is, while we record neurons, we iontophoretically, locally apply our substance by means of a tungsten glass electrode, which is flanked by these two pipettes. So we locally influence our neurons on some trials with the drug, and on some trials, there's no drug applied, and that's why it's the control condition. And I first will talk about cholinergic influences. And the first slide I'm going to show you is just for reasons so you understand actually what we're doing. We have initially a no drug condition, and this slide here shows the first half of the trials of the control no drug condition. The second half of the trials is the recovery condition, and we measure attend RF responses and attend away conditions in the no drug condition. And then we contrast that to trials where we have iontophoretically applied our drug. And as you can see, attention for this neuron increases firing rates, particularly during the late period of the response. And if we apply acetylcholine itself for this neuron, this differential activity was increased. We then quantified this increase by calculating an attention modulation index, which is defined here. And we use different stimulus sizes in this particular experiment. That's why you have attention modulation index for different bar lengths. So those were the stimuli that we presented to the neurons. And you can see that across this, the cells that we recorded from, when acetylcholine was applied, in black, the attention modulation index was larger compared to when it was not applied. This difference was bigger when the stimuli matched the receptor field sizes, but this is not something I'm going to dwell upon in today's talk. So this, we can also quantify that by a different measure, by the ROC, which all of you will be familiar with, and the outcome is more or less the same. When we apply acetylcholine, ROCs are increased, which means that an ideal observer on a trial-by-trial basis could tell more easily where the monkey attends to, compared to when acetylcholine was not applied. And we then also looked at Fano factors when the monkey attended to the receptor field compared to when he attended away from the receptor field as a function of drug application. And when we do this for acetylcholine, you can tell that, these are the individual neurons that we recorded from, in red when acetylcholine was not applied, in black when it was applied. There is no significant difference between red and black clouds. And when we calculate the mean Fano factors as a function of attend away, attend RF, no drug, versus attend away, attend RF, drug, then we find that attention significantly reduced Fano factors in this population of cells, but the drug had no effect on it, nor was there any interaction. So the variance is not affected by our drug application when we apply acetylcholine. In this study, we were also interested in what receptors actually involved in this modulation. So we looked at what happens when we block muscarinic receptors, and we found that muscarinic receptors reduce the attentional modulation significantly. It significantly reduced the ROC values that recorded. But again, it had no differential effect on how much attention reduced the Fano factor. So what you see here is Fano factor attend away, Fano factor attend RF, no drug, Fano factor attend away, scopolamine applied, Fano factor attend RF, scopolamine applied. And there is certainly no significant interaction between drug application and Fano factors. What is surprising here, although, is that scopolamine reduced Fano factors, although it also reduced firing rates overall. And I can't help the data, but it was surprising because I anticipated that scopolamine should actually increase variability. It doesn't, not in these data anyway. That was a very surprising result, which I didn't expect. But it does have no differential effect on the attentional modulation. Although this may seem a bit smaller, that may just be a multiplicative change or whatever. Anyway, there was no significant interaction when we looked at the ANOVA. So we then also looked at what mecamolamine does in terms of rate modulation and in terms of ROC values, and we found that mecamolamine application, which blocks nicotinic receptors, significantly reduced firing rates. So it's not that the drug has no effect. That's an important thing to mention, but the attentional modulation was completely untouched, irrespective of whether we look at the modulation index or the ROC, which is plotted here. And it also had no influence on our Fano factors. So there are real distinctions in terms of what muscarinic blockade does in terms of overall Fano factors. But the important thing to mention here is that cholinergic modulation influences rate changes in acetylcholine through muscarinic receptors affects attention-induced rate changes. It has no effect on attention-induced variability changes. And that is very, very different to what I'm going to show you now in relation to NMDA receptor influences.
What happens to behavior when you do all those injections? Do you see any effects?
We do see effects when we look at the acetylcholine injections, and the effects depend very much on where the monkey attends to. relating to our injection. So if we apply acetylcholine and the monkey is asked to listen to those neurons that we affect with acetylcholine, the reaction time changes are minimal and not significant. However, if the monkey is asked to attend to the opposite hemifield, and he's supposed to listen to neurons that we never influence with the drug, then when we influence neurons the monkey should not listen to with acetylcholine, the monkey is slowed down in detecting changes at this location. You can then say this is distraction, but I would then say a distraction is simply attending to a location you're not supposed to attend to. So those type of effects we see. And when it comes to the NMDA receptor modulation, I'll show you the changes in reaction time. So now what we do again is same approach, but instead of using cholinergic drugs, we apply either APV, which blocks NMDA receptors, or we apply AMPA blockers, CNQX, which affects non-NMDA glutamatergic ionotropic receptors. And when we do that, then we calculate an attentional modulation index across our pool of neurons, then we see that basically the drug application, which is shown on this axis against the control condition, has no effect on attentional rate modulation whatsoever. The rates change, but the attentional modulation of the rate is not affected. When we then look at ROCs, we see that when we apply the drug, ROCs are reduced compared to the control condition. And since ROCs take changes in mean firing rate into account and they take the variance into account, it suggests that NMDA receptors are specifically involved in altering attention-induced variability changes. And we quantified that by, again, calculating Fano factors in the attend-away condition against the attend-RF condition. And in our control condition, again, we find that attention significantly reduces the Fano factor, as shown here. If we now block NMDA receptors, we find that this attention-induced reduction of Fano factors is basically abolished. So we do not see rate changes, attention-induced rate changes when we block NMDA receptors, but we do see that NMDA receptors are very important in helping attention reduce variability. Another way of looking at this is looking at noise correlations. So what you see here is noise correlation from two neurons recorded from the same electrode in the attend-RF condition versus attend-away condition. And attention significantly reduces noise correlation in our sample of cells. And when we then block NMDA receptors, this attention-induced reduction again is abolished. So there are very different features with respect to what acetylcholine does and with respect to what NMDA receptors do in relation to attentional signatures. You could argue that, well, what we do here with the NMDA receptor blockade might be simply due to increased excitation, which I'll get to in a second, but I first will tell you something about the behavior. So, as I already alluded to, it's very important to make a distinction between where the monkey attends to related to where we apply our drug. So when the monkey attends to the receptive field of the neurons under study, then he should listen to those neurons here because they represent that location. And then on some trials we block NMDA receptors and on other trials we don't. And if we do that, then we see that when the drug is not applied, we have so this is the reaction time relative to the grand mean reaction time, so it's a normalized measure. But in this normalized measure, when the drug is not applied, the monkey is faster compared to when the drug is applied. These differences are not huge. They're in the order of 8 milliseconds or something like that. But given that the number of cells that we affect is probably relatively small with the iontophoresis, it's almost surprising to find effects at all. And importantly, when we then ask the monkey to attend to this location, so the monkey should listen to those neurons, but on some trials they affect those neurons, then for NMDA application, or NMDA, not application, NMDA blockade, there is no effect on reaction times whatsoever. So this is highly specific to influencing those neurons that the monkey should listen to. If we influence neurons the monkey should not listen to, like on those trials, there's no effect on behavior.
When you say gland mean, is that separately to left and right heart as well?
No, it's not separately. It's
so there's a real reaction time difference between drug not applied in OF and drug not applied at tender way. The red bar on the left. And the
oh,
left.
sorry. No, it is actually with respect to those things. Yes, sorry. So there is no real difference between these two. There's a real difference between these, and there's none between those. So, as I already alluded to, the question arises, is this simply due to the decreased excitation? Because when we block NMDA receptors, we have reduced excitation. And we did AMPA kainate receptor blockade as a control. And the answer is that some features that I already reported about are also somewhat affected by AMPA receptor blockade, but not to the same extent. So you will already have seen this figure here. These are the Fano factors as a function of attention and as a function of drug application that I've showed before, where attention reduced the Fano factor, and this reduction was more or less abolished when we blocked NMDA receptors. This is the comparison when we blocked AMPA receptors, where you see that, first of all, AMPA receptor blockade increases Fano factors overall. This is different to what NMDA receptor blockade does, where overall there was no significant main effect of drug, so they might be slightly reduced compared to this, but that was not significant. However, here we have a significant increase in Fano factors just due to the drug, and the reduction, attention-induced reduction, was probably smaller, but the interaction didn't reach significance, while here the interaction term was highly significant. And this is not due to sample sizes, because we have actually more cells for this sample than for that sample. Importantly, if we now look at noise correlations, there we see a real complete difference. So the noise correlation, attention-induced noise correlation reduction through NMDA blockade, through attention is abolished by NMDA blockade. As you can see here, you've seen this graph before. If we now block AMPA receptors, then there is the attention-induced noise correlation reduction is still present. But you also see that noise correlations are massively increased when we block AMPA receptors, because excitation is removed, and that's why there's more covariability for whatever reason between simultaneously recorded cells. So overall, this tells you that some features are somewhat shared between AMPA receptor and NMDA receptor blockade, although the effect of NMDA receptor blockade seems to be stronger, while other features are not shared at all.
What's the time scale? This is correlation coefficient between spike counts?
Yes.
What's the time window you use?
So this is 300 milliseconds from 200 milliseconds after stimulus onset until 500 milliseconds after stimulus onset, which is when the first behavioral event could possibly occur. So that's where we terminated. So it's a 300 millisecond window.
Alex, actually, so those values are remarkably high, right?
Well,
even modulation and code is high.
yes, well, yeah, and so there's a distinction between these values and those values, and I don't really know. I kind of know where they're coming from, because in this sample here there were a few pairs which had really high correlation. So one thing here is that these are from the same electrode. They're never from different electrodes, which probably inflates them somewhat. They are almost certainly from, I'm not entirely sure, but I assume they're from layer 2-3, which according to one of the recent Dragoi paper also says, which is where the noise correlations are higher. And there's one thing, so one cell will always be a perfect single unit. The other cell that we correlated with usually is a single unit, but we're not always entirely sure. So if that is 1 or 2 units, then that would also inflate the noise correlations. And that's why I think these are higher than other reports. But I mean, we are absolutely certain that the cells that we correlate are always extremely well separated. And this is already my penultimate slide. When we look at the effects of behavior, you have seen this slide before, only it's now slightly rearranged. So you have made the comparison between attend RF, no drug, versus attend RF drug, where NMDA receptor blockade affects the behavior when the monkey listens to those neurons that we influence with the drug. Here you see that when we block AMPA receptors, the pattern is entirely changed, which also tells you that AMPA receptor blockade is not the same as NMDA receptor blockade. It's not just an effect of excitation. Now we find that actually AMPA receptor blockade slightly, this was just if we just do the comparison between attend RF no drug versus attend RF drug, this was not quite significant, but it touched on significant, the single comparison. However, if we now look at the condition where the monkey has to listen to neurons, is asked to attend to the opposite hemifield, so he should listen to neurons that we never influence by the drug, but when we influence some neurons by the drug, the monkey is actually slowed down to then report the behavioral relevant event. It again is as if the monkey can't help but listen to those neurons he should not listen to when we block AMPA receptors. Why that is, I don't know, but the effect is quite striking. There's a highly significant interaction, So the important take-home message from this slide also is that just because we block excitation doesn't mean that the behavioral effects are identical. They're very, very different. And they are also very different in terms of the signatures of attention that they affect. Right, so to summarize, I've shown you that acetylcholine contributes through muscarinic receptors to attentional rate modulation in primary visual cortex. Cholinergic receptors in V1 do not affect attention-induced variance reduction. I haven't talked about noise correlation reduction in relation to attention because our data set is pretty slim so far, but the data that we have suggests that cholinergic receptors also have no effect on attention-induced noise correlation reductions. So it's really just rate modulation that's affected by acetylcholine. Conversely, NMDA receptors affect attentional modulation in V1 by aiding variance reduction and decorrelation of neuronal activity, not by affecting the attentional rate modulation. So these are completely different effects that two different transmitter/receptor systems induced. So we have a double dissociation between the cholinergic and the NMDA receptor system, and it really tells you that if you can dissociate certain signatures of attention in V1 at the receptor level. What's the final point? Yes, the main contributors, which were Jose Herrero, Mark Roberts, Peter Dayan, Luis De Locato, and Alvin Gieselmann. Thank you very much.
We've been carrying on time. You have time for questions? So I have a question about the behavior slide, which is there's a fairly big effect of whether you're in the RF or not in the RF on the reaction times with no drug. Right? So anyway, no drug is -8. Attend RF no drug is plus.
Yes, but again, I mean, you asked me whether they are, you asked me before whether they are normalized within, and they're not. Okay, so this is normalized against that, and this is normalized against that.
You mostly talked about the response to the stimulus, but did you investigate whether there is any baseline shifts in V1 that are modulated by your different drugs?
Well, the different drugs do induce baseline shifts because they change firing rates. I mean, whenever you tinker with drug systems, you get a change in firing rates.
I was thinking of the attentional modulation.
Yes, no, the baseline firing rates in V1 in layer 2, 3 are so minimal. I mean, we have once looked at whether or not there are baseline changes with attention, and if we pull across all the neurons we ever recorded, then we do see very, very small significant changes which are going from 2.4 spikes per second to 2.48 spikes per second. It is significant when we pull across 400 neurons, but otherwise it's basically not there.
So the response reported was the response to the box, big box, right? What about the response to the little white square?
That's a very good question. I haven't actually looked because, well, I have looked in very early studies, but I haven't systematically looked.
So that's actually the best evidence performing.
Absolutely, yes. Yeah, yeah, yeah.
Have you investigated changes in oscillatory activity, gamma?
Yes, we have. So what we find is that, I mean, do I have time to load up a slide very quickly?
Sure.
Because it's usually easiest to do it that way. Yeah, so this here would show you change what NMDA receptors do to gamma. And so what we find in our task always, but that may be very task specific, is that attention reduces gamma power in V1. We assume that this is down to this task specifics because the monkey really has to focus on a teeny tiny part of the visual field. The change is actually a change of a size of 0.1 by 0.1 degrees in size. So the monkey really has to focus attention extremely to the location where it might happen, and it actually has to do some surround exclusion. And I believe that surround is the most driving force of gamma in V1. When you do surround exclusion, you would see a reduction in V1. It is as if you have less surround stimuli present. Anyway, so this is what we always see in our task, a reduction in gamma power with attention, but this reduction is abolished when we block NMDA receptors. And when we block NMDA receptors, you can see that gamma power is increased overall. And when we block AMPA receptors, this is actually the opposite way around. So the attention-induced reduction is still abolished, but your graphs are really at this level. So AMPA receptor blockade reduces gamma power, and NMDA receptor blockade increases gamma power. Again, it's not just excitation that determines these things. It is which receptor you tinker with that mediates a certain feature.
Have you looked at alpha? Because alpha is like perhaps more relevant to take an NMDA cycle.
We have looked at alpha. So a week ago, I gave this talk 2 weeks ago, and then it was still impressive. A week ago, it was published, and in the paper, you see all the figures in terms of delta, theta, alpha. And I don't want to say something that's inaccurate, so I'll refer you to the paper. Yeah. Okay, thank you.